So my name is Maurice. I am my third year at the University of Baltimore, an in fellow, cohort 3. And today I'm just going to talk a little bit about an analysis I've done on an air quality episode that happened in the Mid-Atlantic region in 2000. I'm not sorry, it's not 2000. In 2021 in May. My advisor is Professor Baltimore, and it's a pleasure to be here. So to get started, this air quality episode for me is being defined by high ozone levels. And so if you're not familiar with ozone, we just have this slide just as a little introduction. So ozone is formed primarily by nitrous oxides and VOCs, all organic compounds. You can see that in the figure on the left. Which comes from anthropogenic emissions from combustion for nitrous oxides, and VOCs primarily come from also anthropogenic emissions and released from plants as well. So ozone is an oxidant, and so it degrades our health and also the environment in marine and with plants, and that's shown in the middle, and into our detriment. And high exposure to ozone can decrease your longevity. And so it's pretty important to study because it's not directly emitted. And so it's formed by photochemistry and is enhanced by dynamics and meteorology. So this event, what I'm showing you here is this is a tile plot from the EPA, and it's showing you, if you read the legend in the top right, the ozone exceedance that I'm talking about here. I circled it in the bottom left corner there, and it shows 3 days of unhealthy for certain groups. And it's kind of peculiar, as you can see from the trend here, that this occurred in May. So it's kind of it's like, oh, this is interesting to study, like what happened here to elucidate the story of why this exceedance happened. And also, why was it so broad? And so in looking at the data, this is the surface data from several sites in just Maryland that I've selected together. And there's a couple of things that you know here. I pointed out three. The first thing is that that's interesting is that there's nocturnal increases. And that's kind of a marker that there's dynamics at play because, as I said before, it's photochemistry. So meaning the sun has to be on ozone to be formed. And so why are there increases happening at the nighttime instead of increasing with filtration? So that in itself brings something interesting to look at. Am I speaking loud enough?
Just a couple higher.
A little bit higher?
Yeah.
Is that good?
Better.
Okay. So there's nocturnal increases, right? And so that's pretty interesting in itself. And that brings the idea that there's probably some dynamics at play because that shouldn't be occurring under normal circumstances. So then the surface ozone, you can see above, I put that black bar there is 70 parts per billion. And I'm designating high ozone as 70 parts per billion for the hourly. And under the National Ambient Air Quality Standards, that the NAAQ stands for, it reaches above 70 parts per billion is when it gets into the chart that I was showing you before, to unhealthy for certain groups and unhealthy for the general public, but only for an 8-hour average. Okay, and so with that, I'm defining high ozone for the rest of the slides as just being an hourly average over 70 parts per billion. And so you can see that happening for 4 days during this event, which is in itself pretty interesting. So this has to be being driven by some kind of dynamics, meteorology impacting the production of ozone. And so in seeing that it's spread all across Maryland, what we can do is we look into some of the profile data that we have. And so what's on the left here is Ozone Lidar. And if you're not familiar with that, it's a active remote sensing technique where we shoot a laser into the sky, and by the absorption of ozone, we can detect how much ozone is there. And so this is plotted in parts per billion by volume. And what we can see, and the white space is just when we don't have data. And what you can see is that during a similar time of the increases that were just on the previous slide, we have very, polluted and well-mixed boundary layer of ozone. And that's in the box that I outlined right there. And it's almost all the way up to the PDL, which you can see from the spectrometer data that's over here. And if you're not familiar with the spectrometer, it's another type of laser. And it's shooting a laser into the atmosphere. And what it's hitting, instead of ozone, it's hitting aerosols. And so we can see that there's a lot of ozone, and there's also a lot of aerosols happening at the same time. So there's some kind of influx of pollution that's come into the area. And this is just a picture for you to kind of visualize. This is the trailer that we use. This is the Tropos instrument at NASA Goddard, and it stands for the Tropospheric Ozone Differential Absorption LiDAR. And it's put in a trailer, it's mobile, and the accelerometer that I'm plotting here, this isn't exactly it, but this is a laser station, so this is co-location. And then in the dynamics of it, you saw the structure, one second. You saw kind of the structure here where you have, and kind of look at this, there's this like wall of aerosols that comes in, and then there's this abrupt change here. And so that's a strong indication of there's dynamics. And so then what's near co-location is at the Howard University Bellows, and that's where we have which is a windy profile. And this uses radar in different directions and a telescope in these buckets to detect the motion of the winds using aerosols. And so similar technique to LiDAR, but in a little bit of different the optical. And so what I've outlined here in the yes, in the black box is the indication that there is some nocturnal dynamics. Right? So this is what's called a nocturnal low-level jet, and what that means is there's really strong winds happening at the night, and that's it's forcing the region to drag some of the pollution upwind, and from us in Maryland, that's going from the Virginia area, following parallel to the Appalachian Mountains. I don't have a figure of it in this talk, but you can imagine it for a second. Going parallel to the Appalachian Mountains and going straight up towards the New York region. And in another slide, you'll see a little bit of the effect of that. You can also see at the time, I don't have it boxed out, but if you look through the 12 to a little bit past 18, you can see the direction of where the influx of aerosols and chemistry is coming from. And that's ESE, that's the eastern southeast region. So so this is what I was talking about, to see some of the spatial context of this event. And like I showed before with the surface plots, those were just only in Maryland, and that kind of sparked the analysis to begin with. But then in looking at the whole network of EPA's like air now system, you can see that this is affecting basically the entire mid-Atlantic region. And so what's plotted here is that these are all high ozone from the surface sites that are there. And like I said, high ozone being above 70 parts per billion. And those are indicated by orange. So you can see in the evolution of the event from the left to the right that it's kind of, you can see it's trailing a little bit. And oh, I'm sorry, I didn't know that's a transition. That's my fault. So it's kind of trailing to outline it for your eyes to see the distribution. And so on the highest occurrence, that would be in the middle. It's pretty broad. So that LiDAR curve, imagine that being spread out through this entire region. And so then I use high split, and I learned that from my old mentor, which was very, very influential experience that I got to get from my NERTO. I hope the audience has heard about the NERTO experience. So I learned about how to do a high split back trajectory, and that's really instrumental in a little bit louder. Okay, that's really instrumental in seeing some of the context on where the air is like moving, where it comes from. So I started the back trajectory, and you can see that in the bottom left. The bottom left corner where you're looking at this is the boundary layer depth at which I started the trajectory, and from the location of the nearby location with where the LiDAR is. And you can see how that air mass has moved backwards in time to try to give us an idea of where it came from. So you see it's circling around the region, right? And it's also, there's some that came from long range transport up into the Canadian region. So that gives us an indication that influx of aerosols is probably from wildfire, because at the time that there were some fires and some smoke that were being transported through the Canadian region. And so there's another instrument that I work with called it's called a Pandora spectrometer. And what this is a passive instrument. So instead of shooting the laser out, it's just a telescope, and it's collecting the light that comes directly from the sun. And it uses that to determine the abundance of ozone that's in the column that it's looking at directly into the sun. And so what I'm trying to guide with your eyes here is that this increase here in the Pandora abundance of ozone is directly proportional to the influx of ozone that happened at the same time. And this is a preliminary one where I'm trying to drag out the boundary portion of that whole column. And I'm comparing it to the boundary layer portion that I've subtracted from the ozone. So that's looking at that what I call the well-mixed PBL, like our planetary boundary layer, and only using that abundance and turning it into the same units to compare it to the measurement from the Pandora. And so the Pandora network is a lot larger than the Ozone Lidar network. And now there's one site in Maryland, and there's another site further down south in Virginia. So the spatial coverage isn't dense enough to actually capture the full evolution of the event, like I was showing you from the entire mid-Atlantic. And so you can use the Pandora network as like a proxy for that. And so that's what I'm trying to pull out in this area. And then along with this, in sort of the next steps is to compare this, begun very preliminarily begun to compare the NOAA GEOS CF model with the Ozone Lidar to sort of evaluate, because currently they don't use the networks from Pandora or the Ozone Lidar to validate the songs. So we give out some more validation using the other instruments. And so this is just kind of here. So the case is driven by the by smoke, by the influx of the aerosols, and also the recirculation of the air in the region from low pressure system or high pressure system, sorry. And It's super interesting because we also have a level of jet that comes into it. So this has been kind of added into my inventory of cases to kind of the characterization of air quality that's happening in advancement. And further work, like I touched on just briefly, is to kind of express more on the spatial temporal variability of this specific event so that it can be translated to other events, and incorporate some other data from Aeronet's system, which they have a comparable network as well. It's actually much larger than either the Pandora or the TollNet, which is the troposphere ozone lidar network, and use some satellites to also capture some more spatial variability. And this should be the slide acknowledgements. Big thank you to me and Cassie for allowing me to do this work, to be funded in grad school, and these are my references. And that is it.